1, go.
My name is Chris Sayak. I'm a student here at Kettering University. I am expected class of 2026. I'm a dual major, mechanical engineering and computer engineering student, and I'm in Dr. Berry's Mech 322 fluid mechanics class. And for my final project, I did wind tunnel design and controls via FreeRTOS. And a quick little project description. Here's a little picture. You can see more later. So I wanted to make a scaled down wind tunnel design. And this included some research of wind tunnel design, actually building it, and then also making the controls for it and implementing that on the physical design. And the reason why I chose this project is I had some personal interest. After we did our in-person flow lab and fluid mechanics, I was really intrigued because I've never got access to a machine such as this one in this room here, and it just really kind of put me in awe, and I wanted to learn more about it. And I wanted a better understanding of why we had it, what they're for, and luckily I was given the opportunity to do my own project for this class. And also at the same time, I was able to implement my skills from my computer engineering degree to make the controls for the project. And I was able to put those together for one challenging, definitely worthy experience. And some relation to environmental issues, as some other groups have mentioned, a wind tunnel can be a great device to measure things in a controlled environment in a lab rather than actually out in the field, such as Corbin's group. They had a car that they could simulate in a wind tunnel rather than actually using fuel on a road to test a car. So some of the goals I had for my project was, firstly, I wanted to understand wind tunnel design better, because there's got to be so much going on with these, which turns out there is. And then next, I want to, I guess, I got a better understanding of the application of fluid mechanics, something in the real world, such as a wind tunnel and what goes into it. And then more on the computer control side, I got a better understanding of a real-time operating system. I got to learn a new programming language, not language, I got to learn a new real-time operating system language and new syntax, and also gain better electrical skills. So there's some background information needed first before I can explain more. The purpose of a wind tunnel, the most basic, obvious one, is simulate items in motion or flight. And you want this in a controlled lab environment where you can control things like temperature, the speed, and other parameters. Some more background is, as you learn in fluid mechanics, the Bernoulli's equation, which is an energy conservation equation. And we can use this in our application to solve for velocity, which we'll get to. Some more background is manometry. And those two things right there, manometry and Bernoulli's equation, those are, you can call it baby math. That's something you learn real quick in fluid mechanics. And with manometry, with the pitot tube especially, you have your stagnation point, which is this point here at A, which is a point parallel to flow velocity, where we can also assume where velocity is 0. Then there's a static pressure tap, which is normal to your flow. And with a little magic, you can combine your Bernoulli's equation and manometry to solve for the velocity of your fluid, which in this case is air. And in this experiment especially, we are assuming no change in height. We're also assuming constant density. And we know that the velocity at a stagnation point is 0. So a little about wind tunnel design. I have some more slides explaining each part. But overall, you have your test section in the middle here, which for mine was 30 inches long. You have your contraction cone. And there's this thing called the contraction cone ratio, which I will explain more about later as well. And then you have your diffuser, kind of like the exit, and then you have open circuit design versus closed circuit design. So what we have here in the lab is a closed circuit design. Everything just flows and keeps flowing. What I implemented, which was a lot easier to do on this scale, was an open circuit design, where you simply just have your contraction cone open to atmosphere, and you have your fan on your diffuser pulling air through. Whereas in the closed circuit design, there's a fan pushing air through the test section. So more about the test section. So my test section is 30 inches long, it's 8 inches tall by 8 inches wide. And I made it out of plexiglass. I was able to find sheets of it on Amazon that were 3 millimeters thick, and this provided a really thin wall, and it was also very smooth, which helped with the friction which I could assume less turbulence with that. And then this 8-inch by 8-inch cross section gave me a 64 inches squared area, which is important for our contraction cone ratio, which we will get more into later. And then also in this middle 10 inches here, we have a door with hinges that opens where you can place items. And then additionally, within the door, there's a small hole cut out to insert a pitot tube. And it's a low quality picture, but it's my test section. You can see little brackets holding it together, our door here in the middle with some hinges, and it's supported on the bottom by a 2x4. And the next is a contraction cone. So this is what mine looked like on paper. Simply a trapezoidal piece of plywood that has 20-inch by 20-inch inlet area, and it's 48 inches long. And then this 20 by 20 inch, like I said, is a 400 square inch area, which compared to our test section gives us a contraction cone ratio of 6.25, which is the area of the inlet to the test section. And ideally, your test section would be curved. I've heard that a 5th degree polynomial is the best for reducing turbulence, such as this one here in the lab. It's very nice and curved, really smooth, which really helps reduce turbulence. Unfortunately, I was not able to implement that from the scope of this project, but it's something to note. And here's a small picture of mine. Like I said, it's just trapezoidal sheets of plywood, and they're spray painted gray to now make it look like plywood. And then lastly, for like the big pieces, is our diffuser, which is on the other end of our test section, which similar size to the contraction cone. This one's only 18 inches by 18 inches at the exit, which is just big enough to fit our fan inside. And our fan is set up as a polar, obviously, that's at the end of our tunnel. And here's a small picture of mine, similar to the contraction cone, spray painted gray plywood. And then next, I needed to find out what size fan to use. So I knew my test section area, and I wanted to find out what volume flow rate my fan would have to be, because those are typically rated in cubic feet per minute. So I had a goal, 35 miles an hour I wanted wind to go, which is 51 feet per second. So I was able to use conservation of mass from fluid mechanics. I knew that my volume flow rate would have to be velocity times area. Then with some basic algebra, I was able to calculate with my specific test section area and the velocity I wanted to reach, what cubic feet per minute I would have to acquire. And I erred on the side of caution and just upsized a little bit to 1650 cubic feet per minute. And here's a picture of the fan that I bought. It's actually a radiator fan for a car. And then here's a picture of it assembled. This is in 2823 AB over in the Computer Engineering Micros lab. And then a little about the controls. I won't dive super deep into the controls. It's not within the scope of this course, but it was very important for the computer engineering side. So as the main controller, I used Arduino R4 Minima, which is Arduino's newest item that came out just this past year, which now has a 32-bit processor that runs at 48 megahertz, which is very, very nice. And I have it running FreeRTOS, which is a real-time operating system. And I had a multi-threaded program that handles all the operations that the user could do. Additionally, there's an LCD screen to monitor information and an RGB LED strip to help display more information. And we had buttons for the user to use. Here's a slight diagram of that. And then more about the display. So like I said, I had a LCD display that would show temperature, stagnation and static pressure, velocity, as well as the user entered manometer information. And then there's the RGB LED strip, like I said, displays the fan speed. And here's a zoomed in picture of the final product. You can see those different parameters listed here in our LED strip. And then next we had 6 buttons implemented onto this. There's a button for turning the fan on and off, one for speeding up, speeding down, switching units between SI units and US customary units, and then one button for changing the digit of what manometer info you wanted to type, and also one button for incrementing it. And I'll explain how exactly that works later. And this is just 6 buttons. This is what the colors they were. And then also, there was motor control and temperature in this project. I used a BTS 7960 motor controller, which gives plenty of room to use a bigger motor in the future. And then also I use a K-type thermocouple with an amplifier breakout module to get a robust, reliable temperature measurement. And then I won't get too big into this either, but the program was broken up into multiple smaller threads. They handled each different operation. And there's one thread for each button, basically. And then for housing all of this into one easy-to-hold package, I 3D printed a little controls box. And this is a 3D model of it I made in SolidWorks. And then this is the first test print, which came out very stringy, not very circular circles there. I was able to reprint it and got a lot higher quality box. And then here I have operation instructions for how to actually use the box to control the wind tunnel. I can explain more during the demo. I'll show you how to do that. And then one future thing that would have been really nice to implement, but I did not have the time to, is the ability to actually log the data. So like the other groups have done, or we did in our lab, was to set the wind tunnel at a specific speed or temperature or whatever parameter you want to do, and then you would write down what you have, which that works. You can type that into Excel. But what would have been better, which would have been very easy, was plug in an SD card. That Arduino spits out all the information that it's currently got, and then when you're done, take the SD card out, plug it in your computer. But I did not have time. That'd be a very easy feature to implement. And then some of the issues that I had with this physical design, which there were a lot, unfortunately, I use rectangular shapes, like I said, for everything, trapezoids and rectangular box. And I didn't have any curves, which wasn't great for flow. And additionally, my contraction cone and diffuser were made from plywood, which compared to, this is what, fiberglass, right, used in the lab here, has a very high coefficient of friction. And I should have had a larger contraction cone ratio, which would have helped get just more volume of air coming into the tunnel. Because I only had a ratio of 6.25 to 1, which that's on the lower side of what's acceptable. You want something higher, 8, 10, 12 for that very large area. And then another big physical issue was actually joining the 3 sections together. As Ray saw about an hour ago, it is not the most stable thing. You look at it wrong, it might, not work as great. I only used brackets, nails, screws, and some liquid adhesive to hold everything together. And then some other issues encountered for the controls is when I was making the different threads for the program, I was running out of memory on my Arduino. So I had to really get neat with how I was making the program. And then also software debugging was very difficult because I had no physical hardware debugger to see what was going wrong with my program whenever I had issues. And also, this project, the controls part of it, was part of a final project for CE 426 real-time embedded systems with Dr. Tawaldi. And we learned a very specific environment in the lab, and I had to port over that knowledge and skills and learn a new environment and new syntax for this project. And then finally, packaging all of that into that small green box that I showed you was very difficult because I'm only a CE. I don't know how to make PCBs, so it was just a big mess of wires. You grab the box and kind of shake it, it might fall apart. Some lessons learned, some future recommendations. I should have done more time researching the design of just wind tunnels and just putting more thought into materials to be used. I should have reached out to different people earlier to get a better idea of what to do. And also more attention to detail to my physical construction. I started running out of time and had to just quickly assemble things, and that showed in the lack of quality of the physical product. Smaller form factor would have been easier to create, and also having a more powerful fan would pull more air. I'd get a higher velocity to study in my wind tunnel.
One quick question.
Yes.
So if this was done over 2 terms, 2 semesters, would you have been able to implement more of those recommendations?
Definitely. The physical design is what needed the most time. The controls part was okay, but the physical design lacked heavily. I'd have more time to research more materials that are still affordable. I could have a better idea of what size I want to use for everything.
So, not to put you on the spot or anything,
No, of course.
but you would be in favor of having a 2-term capstone as opposed to just a 1-term capstone?
Yeah, I mean, there's obviously restrictions on how it can work out, right? So I should have known this before starting the project. Yes.
Yeah, okay, okay.
I knew it was quite ambitious.
But
I definitely learned a lot about the theoretical. I will say that.
ambition's not bad. Ambition's not bad, but okay, good.
Yeah, although the actual result wasn't great, the theory and the time spent and the just principles I had to apply
Well, yeah,
were most important.
okay, all right.
So yeah, just like I was saying, some of the fluid mechanics learning, I got a better conceptual understanding of manometry. Of course, we used it in class. We got to use it in the flow lab,
Yeah.
but just trying to understand how to implement it into a project, I better understand it just in my brain. And then similar to Bernoulli's equation, of course, we used it in the class almost every single day. But seeing how it actually applies, that conservation of the energy of this just wind flowing, understanding that just makes so much more sense. And also I get to see the application of it in real life, such as this wind tunnel. And one of the biggest things is it changed my thought process. Through the lecture and through this project, I get to follow the path better. Because when I first started, it was just start doing something, do something, do something. And then this helped me learn to just sit back, figure out what I need to do first. Don't just jump right in and just plan it all out better.
Excellent.
I do have a demonstration video, but I believe we're going down to check it out. So I'd like to thank my references, Dr. Barry, Ray, Dr. Twaldi from the CE department.
Okay.
Thank you so much. Any questions?
Clap, clap, clap. Any questions? From the audience?
Really good.
Okay, so we have a demonstration downstairs real quick.